Okay, perfect. Hi everyone, and nice to meet you. For those of you that don't know me, I'm Luisa. I'm a third-year PhD student working here at the CBU and at the Department of Psychiatry. And today I'm going to talk about one of my favorite topics when it comes to methods, which is causal inference, and one specific example, direct acyclic graphs. So I thought to structure today's talk into three parts, starting with the three tasks of data science, description, prediction, and causal inference. Then going into an example of when causal inference can go wrong and why, which is the table 2 fallacy. And then talking about direct acyclic graphs, which is a tool that causal inference can offer. So I thought to start giving a bit of context with my journey into causal inference, which started around the first year of my PhD when I realized that my dreams couldn't really come true. In my research, I studied the relationship between social media use and mental health in young people. So I'm passionate and interested in understanding questions about how exposure to different types of contents online or engaging in certain types of social media use then relates to mental health, particularly anxiety and depression. So in an ideal scenario, what we want to do to answer these kind of questions, or in the most simple way, is to use randomization. So we have a randomized design where we draw a sample from the population and then we divide participants into an experimental and a control group. And in this way, what we're doing is spreading out equally over the control and the treatment group the between subject variable, so that the difference between the groups that we get is the average between within person change that is due to our manipulation. However, in some cases, this is not possible, especially with dealing with variables such as social media use, which are much hard to randomize and control. And therefore, this means that most of the times, in my case, I'm dealing with observational data. Observational data either cross-sectional, so at a single time point, or longitudinal, where we look at the same individual over time, if we're lucky enough. And that is what really prompted me to get interested into causal inference and to understand more how can we draw causal inference when working with observational data. Most of the things that I'm going to present on today are things that I learned initially in a causal inference course that I attended in Leeds, which I highly recommend. So for anyone that is interested, feel free to reach out later and I can give you more information. And then mostly reading work by Judah Pearl, which wrote the Book of Why and Causal Inference Statistics and other information about causal inference, both more and less technical. So, starting with setting the stage on the three tasks of data science and why they are different. The first task of data science is description, and this deals with summarizing, describing, and visualizing patterns of the data. So some of us in the room today might be interested in asking description type of questions. In relation to my research, one example could be, how much time daily do adolescents spend on social media? This is different than if we are trying to do prediction, where instead we are trying to identify and discriminate patterns from the data to determine features or forecast events. So we're trying to address questions such as, who is more likely to spend more than 7 hours a day on social media? We're trying to identify a certain group in our data or to forecast an event. We are not really interested in the why or what makes these people more likely. This is instead a goal that causal inference is trying to tackle, where we want to estimate the extent to which changing one factor might change another one. So in this case, we are trying to address questions such as, does opening a social media account lead to clinically relevant levels of anxiety? In other words, if X we go, so my factor of interest, will Y we go, so will my outcome change as a result? And we are really drawing our focus in the focal relationship between our X and our Y. This means that when we do a predictive type of model as compared to a causal model, we inherently have different goals. In a predictive modeling framework, we are trying to predict values of an outcome instead of estimating a causal effect. This means that we are trying to maximize two different things when building our model. In a predictive model, what we want to maximize is our R-squared, or variance explained, whereas in a causal inference model, we want to maximize the accuracy of our estimate. This means that we're going to deal with covariate selection in very different ways. And if you can imagine this in a regression framework for simplicity, but it could also apply to other types of model. In a predictive model, what we want to do is to find the smallest sets of variables that can explain as much of the variance. So we want to balance precision and parsimony. Based on the availability of variables, we want to find what are the variables that are going to explain most of the variance and try to minimize the number of variables so that their joint information can allow a better prediction. This is different from a causal model, where instead our covariate selection is going to be based on external knowledge and judgment. We are going to select variables based on the role they play, because our goal is to minimize the confounding and selection bias, right? So all of the variables that are in our model, aside from our X, our factor of interest, the causal estimand, are going to be there to minimize bias and minimize confounding. This, as a result, leads to the fact that the coefficients in a predictive model are pretty much uninterpretable, in the sense that because the coefficients associated with each variable that you put in the model depend on all of the other variables that are there, you're not going to be able to interpret the coefficient associated with that single variable. Whereas the coefficient in a causal model that is related to your causal estimand hopefully is interpretable, and that's exactly your goal, trying to understand what that coefficient is telling you in relation to your factor of interest. Some may argue, there's debates about this, that in a predictive modeling type of framework, automation is favored. You can use machine learning, throw in as many variables as possible to forecast an event, to identify a certain group, because you don't really care about what specific variables, you just want to maximize their joint information. Whereas in a causal modeling type of framework, it's difficult, if not at all possible, to use automation. And that is because oftentimes you need external knowledge and theory to select which are the variables that are going to go into your model, depending on the role that they play. Okay, so what is then the problem? We often hear about the fact that predictive model and causal models are often conflated, and especially when talking about observational data, what we often see are causal interpretation of prediction models. Where in a paper you would have, for example, a prediction model, here very simply, that looks at the relationship between variables such as active commuting and cancer and mortality, and then finds an association and go on to encourage initiatives to support active commuting as a way of, for example, minimizing a risk of death. Ooh, mosquito. So this is an example of when prediction and causal inference can indeed be conflating, and the possible consequences of that. And it's called the table 2 fallacy. So for those of you that are not familiar with it, it is common to causally interpret multiple adjusted effects estimates from a single predictive model in a single table. So that's kind of the definition, and I'm gonna talk about an example. So this is a paper that you might have come across. It came out in 2020, which of course was the year of COVID, and indeed it was about COVID. So it's a Nature paper that wanted to look at factors associated with COVID-19 related death. So they were interested in which among a lot of factors such as age, sex, obesity, smoking status, ethnicity are related to COVID-19 related death. This paper sparked a lot of interest when it came out, particularly for one of those factors, which is smoking status. Because what it seemed to show is that in the fully adjusted model, smoking status and current smoking status, so being a smoker, was associated with a lower risk of dying from COVID. So smoking seemed to be protective, and this really got a lot of public attention, also Twitter attention, especially from epidemiologists and causal inference people. So the authors were prompted to investigate this further. And what they noticed is that after investigating this more in depth post-hoc, by adding covariates individually to the age, sex, and smoking model, they found that the change in hazard ratio in this coefficient was largely driven by adjusting from chronic respiratory disease. So what is going on here? Basically, in the model where it was shown that current smoking status was protective against COVID-19 related death, respiratory disease was one of the covariates in the model. So the underlying causal structure that was assumed there is that respiratory disease, because it's added as a covariate, is a confounder and therefore is affecting both smoking and COVID-19 death. We know, however, that when we think about the causal structure, that is not the case, and instead respiratory disease could actually be a mediator or a potential mechanism. If you're a smoker, you're more likely to develop respiratory disease, which in turn makes you more likely to die from COVID-19. So by including respiratory disease as a confounder, you're introducing bias in your model. This could be, for example, the result of collider bias. There are different sorts of biases that can come into place when confounders are added and controlled for. Indeed, what the authors did was then fitting a model that adjusted for demographics factors only, which shows a non-significant positive hazard ratio for current smoking. And they then went on to say that this does not support any postulated protective effect of nicotine. So of course, smoking, surprise, doesn't protect you against dying from COVID-19. So this was an example of when using a predictive model type of framework and then go on and interpret the finding causally can result in bias. Okay, so the last part of the talk is going to talk about one of the many methods that causal inference offers, and this method is direct acyclic graphs. Those are also known as DAGs, and they're non-parametric graphical representations of causal relationships between variables. So here you can see an example. Basically, it's a graph. It's not really much fancier than that, but I think it can be very powerful, and I will show you why. So you have the variables, which are presented as nodes. Variables have different roles, and then you have a causal relationship that are presented as arcs or arrows. And it's a non-parametric direct acyclic graph, and there are no circular paths. That's why it's acyclic. Causality unfolds over time, so arrows don't go back in time. So those are kind of like the basic rule for forming a DAG. Usually what you would do is that before you go on and test your model, you can draw a DAG. It's an example from graph theory. You can draw a DAG to then estimate what different roles your variable of interest have. So let's say, for example, here that you want to estimate the total causal effect of a variable C on F. What you would want to do in your model is to keep all causal paths open. This means that, for example, if you know that the variable D is a mediator and sits on the causal path from C to F, you're not going to control for that. You're going to keep the causal path open. Depending on whether you want to estimate the direct or indirect causal effect, you can then decide if you want to do some form of mediation analysis there. What we also want to have is all confounding paths close. What this means is that we want to identify both forms of observed and unobserved confounders and control for them. We also want to condition, which is a synonym for controlling for, competing exposures, such as E in this example, so that we can improve the precision of our causal estimation. So those are one of the principles that you can use after drawing your DAG to then decide how you're going to deal with different variables in your model. So some considerations in terms of using DAGs and thinking about the disadvantages and advantages. In terms of the disadvantages, as you may tell, the word can be a little complex. So the moment you start thinking about causality and all of the potential levels and variables that come into play, you soon get into a very complex space where you might have different constructs and nested within each construct different variables. And the variables have relationship to each other. So there are people that are attempting to do this, and as you can see, you can get to a very complicated DAG. A second consideration is that time really matters, and sometimes the variables that we are trying to measure can be time varying or time invariant. So let's think of an example. Let's say that you're interested in understanding the relationship between weight and sleep. In this case, it's really important to ask yourself, okay, when do weight and sleep, how weight and sleep unfold over time? If we think about weight measured in a morning, for example, it's probably the result of a very long autocorrelated process, right? Whereas sleep the previous night, a bit less so. So in this research question, potentially, unless you use very long time frames, the causality is going to unfold from weight influencing sleep rather than vice versa. Sorry. Another thing to keep in mind in terms of time is that in some cases, we are dealing with time-varying confounders or mediators. So those are variables that are changing over time. For example, affect, mood, some might argue self-esteem. And in these cases, measurement matters. So when you're measuring your variable, it's going to affect what the outcome will be. These variables are much harder to deal with than time-fixed variables, such as, for instance, maternal age at birth, that are always the same and don't change over time. In terms of advantages, I think DAGs, as well as causal inference more generally, can help you integrate theory into modeling, and it really makes you think before starting what role different variables have in relation to each other. And this in turn can really help you to minimize the risk of biases, such as collider bias, that can result for controlling for certain variables that are maybe mediators, as if they're confounders. So I'm very happy to share any of my knowledge and experience using these methods. So that's, in conclusion, Thank you.